In this lesson, we'll review the content from about the first half of Chapter 9. So the first unit we began with was sequences. So determine whether the sequence, as in not infinite sum, not series, is convergent or divergent. If it is convergent, find its limit. So we're going to find the limit as n goes to infinity of 2n squared plus 1 over 3n squared plus 2. So I'm going to divide the numerator by n squared and the denominator by n squared, and that will be the limit as n goes to infinity 2 plus 1 over n squared over 3 plus 2 over n squared, which is 2/3. Technically, if you choose to apply L'Hopital's rule, which you could because we have an infinity over infinity form, you do have to change that n to an x, because L'Hopital's rule applies to functions, and as it stands, your functions are defined for all x's, well, not always all x's, but x's on it within an interval, whereas this is just defined at the positive integers. So officially, if you apply L'Hopital's rule, which is an infinity over infinity form, you do have to use x's. So that would have been 4x over 6x, the x's cancel, and you would have just had, once again, 2/3. Alright, and sine n over n squared plus 1. So one trick with sine is that sine is bounded. It's always in between -1 and 1. So notice that a sub n, we always have that -n over n squared plus 1 is less than or equal to n sine n over n squared plus 1, which is less than or equal to n over n squared plus 1. And that's true because sine is in between -1 and 1. And notice that the limit as n goes to infinity of -n over n squared plus 1, that's equal to 0. And the limit as n goes to infinity of positive n over n squared plus 1 is also equal to 0. So by the squeeze theorem, because n sine n over n squared plus 1 is in between those values, that limit also has to be -1. Or also has to be 0. Alright, for taking a limit as n goes to infinity of ln n over root n, I really would like to use L'Hopital's rule, so I'm going to find the limit as x goes to infinity of ln x over root x. Now this limit is of the form infinity over infinity, so let's apply L'Hopital's rule. The limit, the derivative of ln x is 1 over x. The derivative of root x is 1/2 x to the -1/2, which is the same thing as the limit as x goes to infinity 1 over x divided by 1 over 2 root x, which is the same thing as the limit as x goes to infinity 2 root x over x, which is the limit as x goes to infinity of 2 over root x, or 0. Next, if we have the a sub n's given by 1 plus 3 over n to the 4 over n power, once again I'm going to use L'Hopital's rule, so I'll define a function y equals 1 plus 3 over x, excuse me, that's the whole point, 3 over x to the 4x power. So instead, I'm going to find ln of y's limit, so the limit as x goes to infinity of ln y, and that's going to be the limit as x goes to infinity of 4x times ln of 1 plus 3 over x. And as it is right now, this limit is not something we can use L'Hopital's rule on yet because we have infinity times 0, but I can manipulate it so that I can apply L'Hopital's rule by writing it as ln of 1 plus 3 over x divided by 1 over 4 over x. And now this limit is of the form 0 over 0, so I can apply L'Hopital's rule to find the limit as x goes to infinity. Okay, so the derivative of ln of 1 plus 3 over x will be 1 over 1 plus 3 over x multiplied by the derivative of 3 over x, which is negative 3 over x squared. The derivative of 1 over 4x, think about 1 over 4x as 1 over 4 times 1 over x. So that will be 1/4 times negative 1 over x squared. And the negatives cancel, the over x squareds cancel, and we have the limit as x goes to infinity of 1 over 1 plus 3 over x multiplied by 3 over 1 and 4 over 1. So that limit as x goes to infinity will be 12. So recall that this means that the limit as x goes to infinity of ln y is equal to 12. So ln of the limit as x goes to infinity of y is equal to 12. And now we use e to find the limit as x goes to infinity of y is e to the 12th. So that sequence converges to e to the 12th. Now recall that a series, so an infinite sum from n equals, say, 1, or we'll say 0, to infinity of some terms a sub n is defined as a limit of partial sums, where s sub n is the sum from n, we'll say I equals 0 to n a sub I. So you add up so in this s sub n sequence, the first term is just the first term of the series added itself. The second term is the first two terms added to themselves, etc. And this limit of partial sums is what gives you the sum of the series. Now we had two kinds of series we could actually find the sums of. We had geometric series and we had telescoping series. So this first one is an example of a geometric series. And the geometric series sum was that we had the sum from n equals 0 to infinity a r to the n was equal to a over 1 minus r, as long as the absolute value of r was less than 1. So to apply that formula, you're going to have to change the indexing set here so that this starts at 0. So first of all, also notice, which I think this will make it a little bit easier, 3 to the n minus 1. 2 to the 3n, so 2 to the 3n is the same thing as 8 to the n. So let's change that to 8 to the n. Okay, so this is the same thing as beginning my sum at 0, and then inputting n plus 1 for all my n's. So negative 3 to the n plus 1 minus 1 over 8 to the n plus 1. So that's the sum from 0 to infinity, negative 3 to the n over 8 to the n plus 1, or a sum from n equals 0 to infinity, 1/8 times negative 3/8 to the n. And now using my geometric series formula, my a is 1/8, and r is negative 3/8. So this geometric series does converge because 3/8 is less than 1, and it converges to 1/8 divided by 1 plus 3/8, which if I multiply the numerator and denominator both by 8, that gives me 1 over 8 plus 3, or 1/11. So this next series is an example of a telescoping series. So before we start, we have to use partial fraction decomposition to rewrite 1 over n times n plus 2 as a sum of two fractions. So a over n plus b over n plus 2 is equal to 1 over n times n plus 2. So multiplying by n plus 2, that's a times n plus 2 plus bn will equal 1, or n times a plus b plus 2a equals 1. So this gives us that a plus b must be 0, and 2a has to equal 1. So a is going to be a half, and then b will be negative 1/2. And using this, we can express our sum as the sum from n equals 1 to infinity, 1/2 divided by n, minus 1/2 divided by n plus 2. So before we try to find the exact value of this sum, let's factor out that 1/2. So we'll have 1/2 times the sum from n equals 1 to infinity, 1 over n minus 1 over n plus 2. So let's find an expression for the nth partial sum. So if I add up the first n things, I will just have this 1/2 out in front. Just ignore that for a little bit for now. Now, when I input 1 into that, I will have 1 minus a third. When I input 2, I will have 1/2 minus a quarter. When I input 3, I will have a third minus a fifth. And just one more. If I input 4, I'll have a quarter minus a sixth. So, etc. Now notice how many things are canceling. So this 1/3 will definitely cancel with that 1/3. This 1/4 will cancel with that 1/4. My next term will have a 1/5 canceling that 1/5. The first two terms only have nothing to cancel with. Now listing out the last terms, the very, very last term will be 1 over n minus 1 over n plus 2. The term before that will be, the last portion of it is 1 less than 1 over n plus 2, so it's 1 over n plus 1, and then 1 over n minus 1. And if I were to write one term back, I'd have 1 over n minus 1 over n minus 2. All the stuff in the middle. So you can see that the 1 over n's would cancel, this 1 over n minus 1 would cancel. In general, however many terms are left in the beginning are going to be how many terms left in the end, or how far apart these are. These are a distance of 2 apart. So not really, but you know, the distance from n to n plus 2 is 2. There will be 2 terms on either side. So because of all the canceling things we have here, the nth partial sum is given by 1/2 times 1 plus a half is 3/2 minus 1 over n plus 1 minus 1 over n plus 2. And the sum from n equals 1 to infinity of 1 over n times n plus 2 is equal to the limit as n goes to infinity of these partial sums, which we see is just 1/2 times 3/2 or 3/4. Now, one of the final tools we had in a lesson where we were introduced to series was the test for divergence. And what the test for divergence said is that if the limit as n goes to infinity of the a sub n, so the terms of your series are not equal to 0, then the sum of a sub n's diverge. So let's find the limit as n goes to infinity of ln of n over 3n plus 1. So that's the same thing as ln of the limit as n goes to infinity of n over 3n plus 1, which is ln of 1/3, which is definitely not equal to 0. So thus the series diverges. And just recall that it is not true if you had found the limit as n went to infinity of the a sub n's was equal to 0, that does not mean the sum of a sub n's converges. The typical example of that is the harmonic series 1 over n, so a sum from 1 to infinity. This diverges, but the limit of the terms does go to 0. So the converse of the test for divergence is not true. The next tool we have in our toolbox to determine whether a series is convergent or divergent is the integral test. So before you apply the integral test, you have to assume you have to have a function that is continuous, positive, and decreasing. So generally speaking, continuous and positive are pretty obvious. Proving that a function is decreasing might be a little bit difficult. So, and also, if you're going to use the integral test, you're going to have to actually sort of work out the integral in detail and do that correctly to get full credit. So let's consider the related function f of x equals 1 over x root ln of x. So we know that f of x is continuous from 2 to infinity, and we also know that f of x is positive from 2 to infinity. So 2 is where my series begins. So this function is not continuous, or not defined, let's say, for x's that are negative, but that doesn't matter since we only care about things past 2. And the same thing about the positivity. It's only positive as long as x is bigger than 1, but that falls well within our interval. And actually, decreasing is pretty obvious here because both ln and n are increasing functions. So if you increase the denominator, you decrease the value of 1 over n times root ln n. So f of x is also decreasing. If it's not an obvious example, you'll have to use a derivative and show that the derivative is less than 0, but it's negative, implying the function is decreasing. So when you apply the integral test, just tell me what you're doing. So apply the integral test, and we're going to find the integral from 2 to infinity, 1 over x root ln x dx. So that's the same thing as the limit as some b goes to infinity, the integral from 2 to b, 1 over x root ln x dx. So officially, you can do this integral using a u sub for ln x. You would end up with the integral of 1 over root u du, or the integral of u to the negative 1/2, and that would be 2 u to the 1/2 plus c, of course. But we have a definite integral, so we don't need plus c. So this will antidifferentiate to 2 root ln x, evaluated from 2 to b, or we have the limit as b goes to infinity of 2 root ln of b minus 2 root ln of 2, and this will be infinite, and since our integral diverges, we know that the series also diverges. In this section, the integral test was also used to prove something about p-series. And so recall, if you had a series, so a sum from, say, 1 to infinity, 1 over n to the p, this converged as long as p is greater than 1, and diverge if p is in between 0 and equal to 1. And that is just, you can just say that the function is, or the series is a p-series, and give me the value of what p is. So for example, in this one we have a sum from 1 to infinity. Now the fifth root of n cubed is the same thing as n to the 3/5. So this is a p-series with p equals 3/5, which is less than 1, and thus this series diverges. With the integral test, we also were able to we also had a tool to estimate the remainder when we estimated a series using just the first few terms. So we're going to estimate the infinite sum from 1 to infinity of 1 over n to the 6th using S5. So the fifth partial sum will be given by 1 plus 1 over 2 to the 6th plus 1 over 3 to the 6th, 1 over 4 to the 6th, and 1 over 5 to the 6th, which is approximately equal to 1.0173. Now, the integral test said the error in the estimate is less than or equal to an integral from n plus 1, so in this case 6 to infinity, of 1 over x to the 6th dx. So we have a limit, find a limit as b goes to infinity, the integral from 6 to b, x to the negative 6 dx. So that will be the limit as b goes to infinity, x to the negative 5th over negative 5, evaluated from 6 to b, which is the limit as b goes to infinity of negative 1 over 5b to the 5th plus 1 over 5 times 6 to the 5th. So 1 over 5 times 6 to the 5th is about equal to 0.5 zeros, 4287. So maybe I'm crazy, but that's quite accurate for just using the first 5 terms. The next tests that we had were the comparison tests. So if we had some terms a sub n were less than or equal to b sub n, we had 2 options. We had direct comparison and the limit comparison test. So first of all, what direct comparison said, so there were 2 options. If the b sub n's converge, and also these terms had to both be bigger than 0. That was one requirement of comparison tests, is you had to have positive terms. So if the sum of the larger things converge, then the sum of the a sub n's also converge. That was one option, so that proved convergence. If you wanted to show divergence, you show if the smaller series, if the a sub n's diverge, then of course the b sub n's have to also diverge. So for example, the series that I've given you here looks an awful lot like 1 over n cubed, which would be a p series with p equals 3, and it would converge. So you have to find a series that is larger than this one that also converges. So notice that n cubed plus 1 is bigger than n cubed, and so 1 over n cubed plus 1 is less than 1 over n cubed. And since the sum from n equals 1 to infinity, 1 over n cubed converges, it's a p series with p equal 3. By direct comparison, the sum from n equals 1 to infinity, 1 over n cubed plus 1, also converges. So in the case of these questions, you really do have to give me like a little explanation of why you're proving convergence. So tell me what you're comparing to. You have to have the inequality sort of doing the right thing, because if that inequality had gone the other direction, we couldn't draw any conclusions. And then also cite that you're using the direct comparison test. Now the other tool in your toolbox was the limit comparison test. Now in this case, I think it's not impossible, but it's not easy to show that n plus 1 over n plus 1 cubed plus 1 is less than n over n cubed plus 1. But I don't think that inequality is immediately obvious, because you haven't just increased the size of the denominator, you've also increased the size of the numerator. So you can probably show this directly, but probably not easy to establish that. So maybe the comparison test is not the best way. So let's use the limit comparison test. And we'll let a sub n be the terms of this series, and b sub n be 1 over n squared, which we know converges. And for the limit comparison test, we find the limit of the ratio of an over bn. And as long as this limit is finite, the two series do the same thing. So as the sum of b sub n's will converge, so will the sum of a sub n's. So that's the limit as n goes to infinity of n over n cubed plus 1 multiplied by n squared over 1. So that's the limit as n goes to infinity of n cubed over n cubed plus 1, which is 1. So thus, as the sum from n equals 1 to infinity, 1 over n squared converges, the sum from n equals 1 to infinity, n over n cubed plus 1 also converges by the limit comparison test. The next lesson we discussed alternating series. So alternating series are series of the form sum, maybe from 0 or 1 to infinity, some power of -1 multiplied by some a sub n term. So the terms actually flip-flop negative, positive, or positive, negative. And in this section we also talked about conditional convergence and absolute convergence. So a conditional convergent series is one such that the sum of a sub n's converge, but the sum of the absolute value of a sub n's does not. And a pretty good example of that would be the sum from n equals 1 to infinity -1 to the n over n. This converges by the alternating series test, which we'll review in a moment. But if I absolute value every term, I have 1 over n, which diverges. So that's one example of a conditionally convergent series. There are an infinite number of examples, but that's sort of the typical one. A series that is absolutely convergent is that if the sum of a sub n's converge, so does the sum of the absolute value of a sub n's. So an example of that would be the sum from n equals 1 to infinity of -1 to the n over n squared. This series converges by the alternating series test, and so does the sum from n equals 1 to infinity of 1 over n squared. That's also a p-series with p equal to 2. And one thing to recall is that absolute convergence implies convergence. In other words, if the sum of the absolute values of a sub n's converge, that implies that the sum of a sub n's converge. And we can use that in conjunction with the direct comparison test to show that this series is absolutely convergent. So first of all, this series is not alternating because cosine of 3n will not flip-flop between -1 and +1. It's going to have some terms be positive, some be negative. There's not going to be any consistent flip-flopping pattern, so we can't use the alternating series test. But we can start by noticing that the absolute value of cosine of 3n over 1 plus 1.2 to the n, that's less than or equal to 1 over 1 plus 1.2 to the n, because cosine is bounded between -1 and 1. And then also 1 over 1 plus 1.2 to the n, that's less than 1 over 1.2 to the n, which is the same thing as 1 over 1.2 to the nth power. And 1.2 is 6/5. This actually is 5/6 to the n. And that's because right there what we really have is 1 divided by 6/5, which is actually 5/6. And since the sum from n equals 1 to infinity of 5/6 to the n converges, this is a geometric series with r equals 5/6. We know that by direct comparison, the sum from n equals 1 to infinity of 1 over 1 plus 1.2 to the n also converges. And then thus your original series is absolutely convergent, and therefore convergent. So all that worked to determine that this series was convergent. Now, if your series is alternating, you can actually apply the alternating series test. And for the AST, you have to check two things. The first thing is that the a sub n's must be decreasing. And the second thing is that the limit as n goes to infinity of the a sub n's must be 0. And actually, because it is easier, I would actually check the second thing first. So in this case, my a sub n terms are given by root n over n plus 1. So checking condition 2, the limit as n goes to infinity of root n divided by n plus 1 is indeed going to be 0. Now, checking condition 1, to prove decreasing, let's consider the related function f of x equals root x over x plus 1. The derivative, when you work out using the quotient rule and simplify it, will be 1 minus x over 2 root x times x plus 1. Notice that this is less than 0, it's negative, as long as x is greater than 1. So we know that f is decreasing from 1 to infinity. And so because those two conditions are met, by the alternating series test, the series converges. So if the a sub n's are decreasing and the limit is 0, these two things imply convergence. Either thing not happening, your series will not converge. And to apply the alternating series test, you have to actually show some work and show that you understand that the terms limits are 0 and that the terms are decreasing using either a derivative or some kind of direct comparison between the n plus first term and the nth term. And alternating series test, we also had a great way to estimate the error. In this case, the error is less than or equal to the absolute value of the next term you leave off. So we want to find the sum of this series to within 0.001. So we want our error to be less than 0.0001, or we want the absolute value of an plus 1, which is the error, to be less than that 0.0001. Now, plugging in n plus 1 gives us 1 over n plus 1 to the 5th less than or equal to 0.0001. Now, the best way to figure out the first n that works is just to test various n's. And if you test n's, n equals 6 is the first n that you input, where the value of 1 over 6 plus 1 to the 5th is less than 0.001. 000, yeah. So we're going to estimate this sum using the sum of the first 6 terms. So a sum from n equals 1 to 6, negative 1 to the n plus 1 over n to the 5th. So, and that's about equal to, when you add it all up, 0.97208. The final series tests we had to check series for convergence or divergence were the ratio tests or root tests. And recall that these tests actually test for absolute convergence. So, for this first example, let's apply the ratio test. So we'll find the limit as n goes to infinity, negative 5 to the 2 times n plus 1 power, divided by n plus 1 squared, 9 to the n plus 1, multiplied by n squared, 9 to the n over negative 5 to the 2n. So I'm going to drop the absolute value bars and take out the negatives. So I'll have the limit as n goes to infinity of 5 to the 2n plus 2, n squared, 9 to the n, over n squared plus 2n plus 1, 9 to the n times 9, and then 5 to the 2n. Now just note that 5 to the 2n plus 2 is actually 5 to the 2n times 5 squared. So a whole bunch of stuff is going to cancel here. We'll have 5 squared, because that 5 to the 2n can cancel with the 5 to the 2 in the denominator. So 5 squared n squared over n squared plus 2n plus 1 times 9. Or we have the limit as n goes to infinity of 25 ninths times n squared over n squared plus 2n plus 1. And the limit of n squared over n squared plus 2n plus 1 will be 1 as n goes to infinity. So this limit is 25 ninths. And the ratio test said if the limit of the an plus first term over the nth term was bigger than 1, which this is, your series diverges. So since this is greater than 1, the series diverges. By the ratio test. If we had somehow gotten 9/25, the series would have converged. Remember that when the ratio test gives you a value of 1, it is inconclusive and you must choose a different test. Alright, this isn't obviously a factorial. The numerator is actually what they call a double factorial, so every other odd integer. But let's also apply the ratio test to test for convergence or divergence. When you are testing series for convergence or divergence, make sure you actually tell me which test you're using. So we'll find the limit as n goes to infinity. So first, if we input n plus 1, we'll have 1 times 3 times 5 up to 2n minus 1. And then inputting n plus 1, 2n plus 1 minus 1 will be 2n plus 1. All over 5 to the n plus 1 times n plus 1 factorial. So that's the an plus first term divided by an, or multiplied by the reciprocal. So 5 to the n factorial, 1 times 3 times 5 up to 2n minus 1. Alright, so a whole bunch of stuff will cancel. Up to the 2n minus 1s will cancel. The 5 to the n will cancel. And recall that n plus 1 factorial is n plus 1 multiplied by n factorial. So the n factorials also cancel. So we will have 2n plus 1 over 5 times n plus 1. And that limit will equal 2/5, which is less than 1. So by the ratio test, your series is convergent. It's actually absolutely convergent, but convergent. Now the last test we had was the root test, and we can use that test to figure out what values, so for what values of x will the sum from n equals 1 to infinity, ln of x to the nth power, converge. So let's apply the root test. So we will have convergence if the limit, as n goes to infinity, of the nth root of the absolute value of the a sub n's is less than 1. So the limit as n goes to infinity, the nth root of the absolute value of ln x to the nth will be the absolute value, the limit as n goes to infinity of absolute value ln x. So that will equal just ln x's absolute value. So we'll have convergence as long as this value is less than 1, which tells us that ln x must be between -1 and 1, or -1 e to the negative first is less than x, which is less than e, or e to the negative first is 1 over e. So x is between 1 over e and e. And for those x's, this series will converge.